Okay, good afternoon, everyone. Just going to share my screen. Okay, so I think we can start. This lecture is divided in two parts. So what we are going to do today is that I'm going to go over the first part of this lecture. Then we are going to do some housekeeping, some things for the next couple of weeks. And then we're going to have a break. And then we're going to go for the second portion of the lecture. Okay? So what we are going to cover today is something that is a little bit different from what we have been covered so far, which is like this idea of planning in reinforcement learning. So far, what we have been seeing is that we can generate experience by interacting with an environment. However, there are other ways for us to generate experience as well. Like we humans, we do this all the time. So sometimes we learn from doing things, and sometimes we learn from thinking about things. So planning is kind of like learning from thinking about like actions and tasks, while like what we call learning is when we learn from interaction. And then we're going to see how this plays out in reinforcement learning specifically. So, and again, there are lots of different ways for us to do that. We are going to cover a couple of different ways in this lecture today, but there are way more different ways of doing this, okay? But after this lecture, you will be able to go in the literature and take a look at what people have been doing, and then see how we can improve or how you can improve on these techniques that are provided in the literature. I have been saying all this time that reinforcement learning is what we call model free. So it means that we don't have a model of the environment. We have no model that is required. And instead of like assuming a model, what do, we sample the environment. And then from that sampling, we create an indirect model. So we never actually find a model of the environment. We don't need to find a way that the environment is going to behave for us to actually learn what to do. So this is all implicit. So we learn the value function, but we don't learn what the dynamics of the environment are. So that's one thing that is different in reinforcement learning. And we have seen that there are other methods that are what we call model-based. So this means that we assume that we have a distribution that describes how the environment behaves. So we have some type of mathematical modeling. Most of the time, in this case, we are going to have equations that are going to tell us how the environment is going to behave in an stochastic sense. So we do have like probabilities that describe what is going to happen in this environment when we execute this particular action in this particular state. So then we have like what this transition is going to be. Note that this can also be done in other ways. So if you are, in electrical engineering, or if you are in mechanical engineering, you probably have seen that you can model lots of different systems by using differential equations. So a representation based on differential equations, specifically when we have stochastic differential equations, can actually be used to represent this environment. And then from that representation, we can generate decisions on how we are going to deal with the environment. And this, we have been doing this in engineering for over 100 years, and like in a systematic way. And we have been doing this in science for hundreds of years, right? So this is something that is very powerful. It works really well, but is predicated on the fact that we can derive these particular solutions from first principles. What happens when we cannot do that because of maybe the environment is too difficult, like too complex. Maybe the environment is going to be too uncertain, right? So we don't know for certain what the environment is. So what happens in that case? So today, what we're going to see is that in reinforcement learning, we can try to unify these two representations. So we do have a model-free type of approach. However, we try to somehow identify and extract a model from this environment. And again, there is a whole area of investigation that is called system identification that does that. But system identification assumes that we have like a different types of models for the environment. We are going to talk about a few of them today, but in general, this can be done with other methods. Yes, there's a question.
Yes, doctor. In RL, there is any approach that following the mix between model free and model based?
Which one? Sorry, which model you're referring to?
A hybrid model between the model based and the model.
Yeah. So when you say like hyper modeling, are you referring to like a meta modeling, or it's a model that can represent several different models?
That can support the free model or model free. We can make model based to support it.
Yeah, so that's the idea, right? So that instead of using just a free sampling of the environment, so we are going to create a model that is going to bias the way that we are going to sample the environment, right? So I think it's that's exactly what you're talking about, right? So instead of us like blindly sampling the environment, we are going to create a model that is going to guide the way that we're going to create this sampling. So we are going to make the sampling more efficient. That's kind of in line with what you were saying, right?
Right.
Okay. Yeah. So and there are lots of different ways of doing this, right? So nowadays, one of the most powerful ways of doing that is by us creating a scheme of the model, and then we don't know what the parameters of the model is going to be, and then we create like a different modeling capabilities of that particular environment. So that's like sometimes people mention that call that like a meta model of the environment, but I think that it's what you say as a hyper model of the environment. So I guess that it's both can be used in the same sense. Okay. So what do we want to do then? So what we want to do is to create a model. Okay. So we're going to derive a model, and based on this model, we are going to create a different sampling strategy so that we can derive a better policy. So that's the idea here. So from the model, we are going to create a sampling, and to this sampling, we give the name planning. Okay. So again, maybe you have seen like planning in other areas, right? So this is very common. If you are in engineering, usually you're talking about like a motion planning, task planning. If you're in computer science, you're talking about like these formal methods like for planning. So in this particular case here, so what we are talking about is a computational process that is going to create a model that is going to relate the inputs to the outputs. And then based on that, we can create a better sampling of the environment. So that's what the sense that we are using it in here. It is different from like other areas of planning, right? Because in other areas of planning, you have like the search that is going to be done in a very formal way. So in this case here, you're doing planning from a sampling-based type of way. So, and again, if you have done like robotics, so you know that there are planners that take into consideration the structure of the environment. Like for example, there is a technique called A star. right? That if from that particular node on a graph, you can actually find what is going to be the best way for you to reach another node in the graph. That's based and predicated on the fact that we have this representation of the environment that exists a priori. And there are other methods that are called like sample-based methods. Like, for example, one of the most common one is called RRT, where you sample the environment. You create like on the fly dots on this environment, like points on this environment, and then you see like through like certain rules if you can reach that point or not. So this is similar to what I mean here by planning. It is not like the first type, right? So we don't start with directly a model of the environment. So we are going to derive this model of the environment through sampling, and based on that, we are going to create a better sample process for this environment. In AI, there are two different types of planning that people usually refer to. One is called the state space planning. So this means that we have a search through the state space. So, for example, this is sometimes done like for motion, right? So you have like a vehicle, you have, or you know, these big robotic arms, specifically those that go like to the space station. So you do try to find in the state space what would be the best policy. So this is the type of planning that we are going to deal with in here, right? So that we go through the state space and we create a plan for that. Different from these other planners that I'm referring to, this, in our case, we are not going to do this based on like a very complex equations or things like that, but we are going to do that through an approximation of the environment. Nowadays, like one of the powerful ways of doing that is through a neural network, right? So you can actually get a neural network to identify a model of environment. Why? Because the neural network is going to be a universal approximator. So you can approximate that model. But regardless of the way we are doing this, and here we are going to be agnostic on the method that we are going to be using. So we can actually do that. It could be that we are trying to approximate like a model of environment through the structure of the environment. For example, let's assume that we know that this particular environment or this agent can be represented as an ordinary differential equation. So then the problem becomes how we are going to identify these different parameters of this equation, right? But in our case here, we are going to be agnostic of that. I'm going to mention a few techniques today, but it's later on, namely after your break, we are going to see all of these different models in more detail. Okay, there is a different type of planning. That is when we transform a plan from one space to another space. And this is like one typical example of that is like evolutionary methods, like genetic algorithms. So in that case, we have a space where we actuate, and the plan itself is going to be represented in a different space. In that particular case, if you're familiar with that, is going to be like the different chromosomes that are going to represent possible solutions in that particular environment. So the chromosome is an encoding of what the solution is going to be. And again, you can do this in this particular environment here in this particular way. However, it's usually more cumbersome, and then it's not going to be as sample efficient as these other methods that we are going to talk about today. But it can be done. And again, if you go like to the literature, you will find it. You will find people that use evolutionary methods in conjunction with reinforcement learning to solve for these problems. Okay. In our case, since we are doing these state space plans, what we are going to do, we are going to do this in two different ways. So we are going to try to compute the value functions, and this is going to be an intermediate way to improve the policy, same way as we have been doing so far. And then we are going to use the model to create a faster way for us to do the updates in the values. Okay, and Third thing is that we are going to mix this with real interactions with the environment. So we are going to have like these two different strategies that we can actually explore here. So from the model, we are going to create simulated experience. So this simulated experience here is going to be experience that we can use to create better sampling of the environment. Since we are creating this better sampling of the environment with the simulated experience, we are going to see that this is going to have an impact on the way that we are going to acquire information in real life. Okay. Then from all this simulated experience, we are going to create new values. And if you recall, there are two different ways that we have seen this. So it's a V function that is going to be a function of a state, or, and we have discussed this before, we can do one or the other. We can have a Q function that is going to be the state action pair, right? So we can do one or the other here. And from here, we are going to create a better policy. And this policy is going to impact how the model is going to be represented. And it is going to also impact the way that the sampling is going to be done. Okay, so we are going to see these different steps today. And this is a very powerful thing that have been used, that we use quite a bit, right? So it's it is something that you find in the literature and in real implementations quite often. Okay, so the idea here is that planning is going to be done over simulation. What does that mean? This is not that we are going to be using a simulator, like a physics simulator, or I don't know, a video game or whatever. It's not that. This is going to be, let's call it fictitious experience, right? So it's experience that is not extracted from the interaction with an environment. If you have a simulator, let's say a simulator for like a physical application, let's say a car. So that is in fact your environment. The simulation here is you are going from the model, generate an output just based on what you have acquired so far. It is not going to require an interaction with the environment. Why is this actually important? Because even if you have a simulation, like let's say a physics simulation in your computer, that's going to take resources, that's going to take time. You're going to need to generate these samples from interactions with the environment that are going to occupy cycles in your computer, right? And most of the time, it's a lot of cycles, right? If you're talking about real experience, like meaning that you're going to interact with real systems, I don't know, a robot, a network, like other agents that are playing games, whatever, right? So that's going to take way more time, right? Because you're going to have to interact with the real world. And then this is going to take time for things to be computed and for things to be changed in your environment. So there is a very striking difference between simulation and experience. But here, simulation means how we are going to simulate this environment in a very fast way, right? Through a model that we acquire from this environment, and not necessarily from interacting with this environment, either virtually, like through what we call a computer simulation, or physically, like when we access the agent directly. And the other thing is that we can interchange these methods, and we can combine these methods. This is something that is done very, very often. Why? Because once you identify a model, you have to always consider the possibility that your model is not fully correct. And the only way for you to test if your model is correct is by still having real experience. So the real experience is going to be the arbiter of the success of your approximation. Okay, so you still need to do that. Otherwise, you could actually just be hallucinating, right? So, like to use a term that is that people use nowadays for kind of this type of behavior. Okay, this means that there is a mismatch between your model and the real experience. So you still need to have real experience to ground your model into reality. Okay, so what do? We are going to select a state, and we're going to select an action, and then we are going to send this state to a sample model. And this is a probabilistic model that is going to tell us, if I had this state and this action, what would be my reward and what my next state would be as well. Okay, so I have two things. And since now we have all these different values here, I can do a Q-learning step that is like this equation here. Observe that this is derived from the model, okay? And then this, like the next state, is going to be derived from the model. And we are going to update our real value with this information that is generated from the environment, from the model, sorry, not directly from the environment. If we show this in a diagram, what we are going to do is that sometimes we are going to have this value policy that is going to generate an action. This action is going to create like actual experience. This experience is going to be used for two different things. One is going to generate like a direct reinforcement learning loop. So it's going to change the value function directly. The other, but it's also going to be used at the same time to learn a model. So we are going to be able to derive a model from this. Once we have this model, we are going to generate planning, which is fictitious experience. So it's going to be something that is going to be generated from the environment itself, okay? From the model itself. And this is also going to impact the value. So there will be 2 points of update in this value. And this is going to generate different policies. Observe that the policy will only affect the real experience. And the real experience indirectly is going to generate the model. So that's the idea here. And again, this has been used in other areas as well. But basically what we are doing, we are creating a way to encode our experience with the value in this indirect way. And you can think of this, right? Okay, so how can we generate this? We can generate this like by creating an approximation of the model. We can, like, for example, if we have the format of the model, let's say that we know that this is a vehicle. We know that this vehicle is going to be like a third order system. So we can create like an approximation of that model, and then we can create that as the way for us to generate the sampling. We can do this as a neural network. We can do this, like nowadays people do this all the time, with a large model, like a large foundation model of some sort. So it could be a large language model. It could be a vision, like a large model as well. It could be sometimes like a dynamic foundation model. It could be lots of different things, right? So, but here, what we are doing from the experience, we are going to create a model, and then this experience is going to be used to tune this model as needed, as necessary. To this technique, we call it indirect reinforcement learning, because now we have direct updates. So this is a direct update here. And we have indirect updates through the plan. Okay, so one is going to be direct, the other one is going to be indirect. There is a technique that is called DyNA, like DyNA learning, right? So, and it's usually applied to Q learning. So that's why it's usually called DyNA Q learning, but it can be used in other things. Is that here you have an environment that you're going to to interact with. So it's the same diagram as the one before, but in this case here is just to make it clear that you have two different loops. One is the direct reinforcement learning loop, and the other one is going to be the indirect one that is going to be done through simulated experience. So from real experience, we are going to acquire data from the environment, and then we are going to apply this to a model, and then in that particular model, we are going to find a better a representation of simulated experience. And this simulated experience is going to update the policy as well. Okay, so we are going to have these two different updates here. This is one update, indirect, and this is the other update that is direct. Note that you can actually have different loops for this. Of course, that since you are simulating experience, you can actually do this way faster than with direct reinforcement learning. Okay, but you can also say that the direct updates, they are going to be more meaningful for you, right? Because they actually represent interaction with the environment, while the simulated experience, they don't, right? So like, for example, you could actually have like one learning rate here, let's say alpha, and another learning rate here, let's say beta, okay? So if this is one thing that you want to do, and then you see in the literature that people have done this in the past, okay? The algorithm is, it's kind of simple. It's not very complicated. So here again, we are just assuming that we don't, we are model agnostic. How this model is being updated is not important for us, okay? So for now, we are going to get there. But for now, this is not important. So basically what we're going to do, once we have a model, whatever that model is going to be, we are going to be able to take a real action in the real environment. We are going to be able to observe a real reward, and we are going to be able to observe a real next state. With that, we do one cycle of reinforcement learning. This is what we call direct reinforcement learning. Then we are going to be able to use that information to train a model, right? So this is the training of the model. So here it's assuming a deterministic environment, but it does not need to be that, right? So here I'm agnostic on how this model is going to be approximated. Then I'm going to create this loop, because this portion here is going to be much faster. Observe that taking an action, finding a reward, and waiting the system to move to a new state takes time. It takes effort. It takes resources. While if I have a model and I just create this does not take effort, okay? So it's the same thing when you're when you're imagining things, right? So for example, sometimes you are really studying something, right? So you are, I don't know, like trying to solve a problem in a lab, for example, right? And things, they take time. But once you have a model of what is going on in your head, you can think of what is actually going to happen when you do something. And then you can learn from that as well. Here, that's what this indirect version here is going to do, okay? So this is going to be the indirect. Actually, the indirect is this portion here. So you're going to learn from this indirect information. Note that it is possible that this is incorrect. If this is incorrect, what is going to happen is that at some moment in time, you're going to try that again in real life, and this is going to change. Once this changes, so then this update here is also going to change, okay? So that's the idea. That's how this indirect learning happens. However, we can run this like n times, while here, maybe we can only interact with the environment once. So we speed up things. So we have like way more opportunities to do the updates. Let's see this in an example. So let's assume that we have this situation here. And let's assume that we start here and we want to get to this goal. You should, you know by now that what is going to happen is that randomly we are going to change actions here up to the point that we get to this state, and eventually we choose the action to go north. Once this happens, we got to the goal the first time. But all the way that it takes us to get to this point here, this was still this is still all random, right? As time goes by, we learn that from here we need to go north, right? That here we need to go north and backwards all the way to the first state. This takes time, but if we have this information here, and for example, we have this last information here, we have this. When we get to this point here, and we know that this particular update would be more beneficial for us, we can imagine, oh, if I'm here, instead of going south, I would go north, and this is going to be beneficial to me. And therefore, I'm going to speed up this learning, because now you're imagining or you are using this information in a way that can speed up the interaction they have with the environment. Okay, and you can see this in real runnings of the system. So let's assume here that we have direct reinforcement learning, or we have planning steps for reinforcement learning. So here, the episodes, they refer to real interaction with the environment. Whereas the planning steps means that you're going to have more generated information in this indirect way. So here, in 10 episodes, if you have 50 planning steps, you had way more steps here, right? However, for interaction with the environment, you have way less interaction with the environment. The same interaction with the environment, but note that there is a very big difference between what the number of steps per episode is going to be here and here. So this happens because we are able, from that environment, to generate this information, extra information, through the model, okay? And then we can actually make this faster. Of course, that if you have more planning steps, you would get a more interaction with the environment, but at a cost, right? Because this is going to take cycles of your computer as well, and more memory as well, okay? So, but it is going to be something that is going to be more beneficial. If I show you that same problem again on a table, you're going to see what I'm talking about. So in this case here, if you have no planning, only the last update is actually going to be meaningful to you, right? Because it's the one that generated a reward that was different from whatever you had before. However, now that you actually had all this information before, you can use the model and you can regenerate all these different updates here, okay? So now, in one cycle, you can actually take into consideration everything that has happened before. One caveat here is one thing that we are assuming is that this environment here is well behaved, meaning that it does not change over time. Another thing is that this particular update is in here, this actually goes much, much faster because this environment is deterministic. If the environment is not deterministic, you're going to see the same noise that you see here in the direct reinforcement learning into the planning steps as well. And that is a trade-off, right? And I'm not claiming here that you should always use these planning steps. But in situations where interacting with the environment is very costly, you might consider using this. And this is something that people use quite a bit. I do use this in my research. So there are different ways that we try to use things so to make the interaction with the environment less costly. And this is something that is important. It is something that you should take into consideration in certain situations. DynaQ is one way for us to do this. There are different ways as well. Okay, so this is just one way for us to do that. So we are going to see like a different way of doing this now. That is something that might be better than DynaQ. The problem with DynaQ is that if this is stochastic, or if this takes into consideration environments that are more complex with more actions, for example, this might be a problem because now your information is going to be equally generated. Notice that we are assuming here, and then I go back to the equation here, is that I choose these states randomly and I choose the actions randomly. Okay? But this is not necessarily a very good thing, right? So we could actually try to use this in a different way because now we have more information on the environment. So instead of using this very inefficient way that we are just going to randomly sample things in a way that is, like in that case, is implicit, that is uniformly distributed. So we are going to do this in a using information that is going to be more realistic to the environment that we are going to deal with. Okay, so we are going to try to use this in a way that is going to increase our chances of getting a better update. So we are going to prioritize certain actions over other actions. How do we create these priorities? So this is one thing. So how do we create this? So one way of us creating that is for us to relate the priorities on the TG error. So if you recall, last time we called this the TG error. So this is going to be a delta T. Sorry, there's someone with the microphone on.
خالد فاتح. طب ما كنت بتقفل السلك يا خالد.
Hello. Okay. So could everyone please turn off your microphone? Okay. Just give me a second. Okay. Okay. So this is like what we call like our TG error. This is the delta T there. Okay. So this TG error is going to tell us how wrong we were. So if you recall, we defined this as being the target minus the estimate, right? So if we are wrong, if the target is very far from the estimate, so this is the estimate, and this other quantity here is going to be the target. It means that when we do this update, this is going to have a much bigger effect on the updates. So now, if this value, if this P is greater than a threshold that we define, we are going to put this into a queue, okay? And this queue will have a priority P that is going to be this value here. If this value is larger, we are going to actually use it more often, okay? And then when we loop over all of this, instead of just randomly select things, we are going to select from the queue, from this priority queue. This means that we are going to give priority to updates that are going to change our queue values more, right? because observe that we are going to use the same alpha in everywhere. Okay, so now we are going to do this. But moreover, once we do this update, we are going to also get an updates from other states, right? So because now, since we updated S, we need to also consider all the other states that are going to lead to S. And then we're going to do this again. And then we are going to create like these nested priorities. And then we are going to use the same values like to see what is going to be the effect of the changes. So if you consider again this problem here, when we don't have planning, that's what we have, right? If we have planning with DynaQ, we are going to select all of these randomly. Now, the ones that actually gave me the biggest updates, right? So in this particular case, will be like the ones that are closer to the goal. They are going to take priority. And now we are going to order the learning from whatever gives us the biggest updates to the ones that gives us the smaller updates. But observe that once we keep doing this for these big updates here, these are going to get smaller. And these other ones here, let's say, that are close by, are going to get stronger. And then we do this by areas. But this is going to be based on the sampling and then the way that we are going to solve this problem. Okay, this is a very powerful way for doing this, and there are lots of different ways, and we are going to see this like later on in the course. Lots of ideas that take this into consideration to create a better sampling efficiency of our environment. One thing that you should observe here is that by using prioritized sweeping, we get like a big gains compared to DynaQ that is just randomly used, okay? Here, looking at this, you may think that this is small, but observe that the scale here is a logarithmic scale, right? So this is actually a huge difference. So you're talking about like a difference of, let's say here, almost 10 to the power of 7 to something that is going to be one order of magnitudes like lower. So this is big, okay? So this is very, very big. And this is something that we can take advantage of. So we can speed up learning by doing this. Nowadays, one way of doing this sampling is by using, as I mentioned before, a foundation model, because the foundation model is going to create these generalizations for us as well. So this is a very good area of research as well. And then there are different ways that we can actually do that, okay? If we look at, and this is something that I mentioned last time, that there are different ways for us to do these updates, right? So we can do these updates by sampling. And this is like this way here, right? So we create these trials or these trails. And the other way is for us to do these expected updates. By now, you should understand that these two different things, they are different, and that if you don't know anything about these probabilities here, this sampling idea is way more efficient, okay? And we can do this like in SARSA, we can do this in TD learning, we can do this in Q learning, and there are lots of different ways that we can do these updates. Now, I showed last time that there are versions of these updates that we can do like with the expected values, okay? The question is, are these better than sample updates? So one thing is that they will not have sample bias. So if we know how we are going to sample, So this is going to be better, right? Because now sample bias means that we are going to randomly select like a different trial. And this may have some effect on how we are going to behave, okay? However, they are way more computationally costly. And as we saw last time, this also depends on how much I can actually trust this. If I can trust this, so this is going to be better. If I cannot trust this, so this is not going to be better, okay? And there is a computational cost that is not negligible, because now we do need to consider the summation here. And here, like just to give you a feeling of what this can be a huge number. So the number of combinations of next states and next reward that you can actually observe can be very, very big. When I say very, very big, let's say in a video game, because there are other things that are random in your environment, we can be talking about like hundreds or even thousands of iterations here. Of course, that if you're going to do this in your computer, this is not going to be very efficient. And the other thing is that you may not be able to do this on a GPU, because like each one of them is going to be different, and the calculations may be different for each one of the ideas there. Okay. If this branching, therefore, like if the number of possible next states is very, very large, this number of operations is going to be b times that number. So if it is 1,000, it's going to be 1,000 more operations. And this may be very complicated. The other thing is that like when you are going to propagate these updates, this is going to take much, much longer, right? It's going to be much slower when you have this expected update case, because now you have to consider all these different considerations, okay? This means that we can create a better way for us to do this by mixing these different ideas, but not considering the whole sweep. So this is another idea that is very, very, very efficient, that is called trajectory sampling. Later on in this course, I'm going to show you some examples of trajectory sampling used in both video games and robotics. But just keep in mind that what we are trying to do, we are trying to create a better update, right? A better way to do these updates that are going to be created from the information that we already have at the environment, right? So this is something that we want to do. It's very similar to DynaQ, but it is going to be created compared to trajectories that have already happened, right? So these trajectories, like in DynaQ, we just randomly select stuff. Here, instead of like sampling just one point, we are going to sample the whole trajectory. So we are 100% sure that that has happened in the past. And then we can actually use this as the experience that we can generate, right? Because it's very often that experience is not going to be generated just in one point, right? It's going to be generated in more than one point, in more than one way. So things are going to be dependent. So you create one point, and then from that point you go to another point, and so on and so forth. If this has already happened, you know with probability 1 that that's a possibility. So this is what we do in trajectory sampling. So yes, so we can do better because we are going to use the policy that we have that it already generated the information. Okay, so we are going to sample based on the policy that has already created this particular experience. So we are going to start from somewhere, and this can be arbitrary, and then we're going to say how long this experience is going to be. So we are going to say that, let's say, we are going to do this for 100 steps. And then we are going to create this information, and then we're going to save this. And based on that, we are going to follow this policy for a while, okay? And we will see that this is the way that modern systems do this. Like, for example, if you're going to develop a system for learning in a game, in a video game, this is exactly what you do. If you're going to learn, like create a system for robotics, that's exactly the way you do it, right? Because these are systems that are constrained. So for you to go from one state to the next, you have to consider these possible paths, okay? So we are going to start at one point, and then we're going to follow it for a while. Either we say that we're going to follow this, as I mentioned, like 100 times steps, or we can say, well, follow this all the way to the end, right? But this is going to be done based on experience that you generate. And then these trajectories, we are going to perform the updates on these trajectories directly. Now, observe that we can do this in a sequential way. So we can go from the initial point, all the way to the end point. And this is all fine. You can do it. But modern applications, you do this as a batch, right? The trajectories, they are going to be batches that are going to be learning from. So, but they are going to be based on real trajectories that you can actually follow. So this is what we call trajectory sampling. And there are lots of different ways to create these trajectory samplings. Okay, but there are a few questions. So the first question is this online policy a good choice? The question that you have to ask yourself is, if I don't use this, what should I use? So if you're not using the policy that you already have derived and that is going to generate your experience, what could you use? And the answer is random sampling. How random that it's going to be depends on how much you know about your process. So I'm not saying here that the random sampling is always uniformly sampling, right? But it can be like a bias sampling of some sort, like a Poisson distribution, whatever, right? If you have more information of that environment. But regardless, it is something that is going to be random. And you do not know if that's actually possible or common or not, okay? So that's one thing. Therefore, given the constraints that we don't have access to what the system is able to do, online policy as a way to generate our trajectory is very, very powerful. It is possibly the best way for us to do it, okay? Are there risks? And you should be thinking that, yes, there are risks, right? Because what happens if my trajectories in the beginning, they are not trustworthy? Even though like they were generated, but it could be that they are actually bad trajectories. And then you can actually get stuck in that loop because you get stuck in these bad policies. And then in the limit, you can get stuck in certain parts of the state space. And this may be extremely problematic for us, okay? Again, there are techniques for us to be able to avoid this, but it is something that you should understand. That is a risk, right? Because whatever solution that you have found so far, it is probably not the best, right? But the idea.
Neural networks and back propagation, which is actually the process. Earlier,
Hello.
I was studying this. I was often referring to it as the magical process. That,
just a second.
Lets the neural networks learn from their own mistakes, pretty much like humans, but.
Okay. I'm going to ask you, like, don't know, if you don't have a question at that particular moment in time, just keep your microphone off, right? Because sometimes it's just very distracting that there's different sounds. Okay. So that's one thing. So we stopped here that it's we know at least that that exists, but there is a risk that we are going to get stuck in that particular area. So let us consider an example. Let's assume that we have a probability 0.1 that the expected reward is going to mean like a 0 and variance 1. Also, there is a probability of 10% that we are going to reach a final state in each transition. And then, based on the number of branches that we are going to have, so how trajectory sampling is going to be more efficient, okay? And here it is like for 1,000 states. You see that if you have the branching is very small, so on policy is going to be way better, but which makes sense because we just get over like, I don't know, that particular, we generate information in a much faster way. But for whatever other solution that we have, we can actually see that the early updates, they are actually very beneficial. And then don't let this value here, sorry, this difference here, trick you, okay? Because even though there is a difference here, most of the time, and if you recall this, most of the time, what you want is like early updates, right? So here is going to be the value of start state under this greedy policy. So even though like the uniform is going to give you these better values here, observe that the rise is going to be much faster. And this rise that is going to be much faster in more complex environments, because this is a very small environment, like 1,000 states, this is actually not going to be the same. Because if you have 1,000 states, yes, eventually when you have enough number of updates, you're going to visit everything. This means that you're going to be able to visit all the states with uniform, and on policy, you're not going to visit all the states. But this is only 1,000 states, okay? In reality, if I told you this before, you're talking about millions of states or billions of states, okay? In those situations, the uniform will not be able to cover the whole space. And here is just for you to see that even when you have 10,000 states, which is not a lot, so now the uniform is not going to be able to outperform the on policy. So on policy, it is going to be way more efficient. And when you increase the number of states and you increase the branching factor, so you're going to see an even more pronounced difference here. So imagine that you're going to do uniform sampling to solve like something like a chess. So this is eventually going to be extremely inefficient because you're just trying to solve things with data that is not trustworthy. You cannot trust that data, okay? So keep that in mind, okay? But based on these ideas, so we can actually take a look at the different ways for us to solve these problems, right? In reinforcement learning, we are mostly in this area here, okay? So this is where we are. So we don't have a lot of, the updates are not going to be very wide. And we can actually go very deep, right? If you go Monte Carlo. But we are in here. We are not expanding the updates. Even when we are doing these expected values, right, these expected updates, we don't do this for everything. Why not? Observe that when we do this for a single step, like when we do this for dynamic programming, this might be efficient in the sense that we are going to transform the problem into a polynomial problem, okay? but this polynomial may be very complex. Okay, this area here, exhaustive search, that is where we can guarantee that we have an optimal solution, is prohibitive for most of the cases. Okay, so we do need sampling, and then the depth of the sample is going to dictate how much information and how fast our updates is going to be. We've seen two different ways of doing this. One is called Monte Carlo, to which we go all the way to a terminal state. And the other one is temporal difference, and it specifically one step temporal difference, where we just do this for one step, just this step here. I mentioned last time that we can do this for more than one step, right? So we can have a 2 steps, 3 steps, 4 steps, and so on and so forth, right? And this can actually do this in different depths. After the break, what we are going to see is a way for us to formalize how we can transform from TD learning to Monte Carlo learning. So transforming and then creating a mix of both. Okay, so that's what we are going to see next time after the break. And another thing that I want you to pay attention to is that this gives rise actually to very efficient ways to do updates in neural networks. That's what we are going to see after your vacation, right? And it's also something that you're going to see next lecture. As I mentioned, next lecture is going to be a tutorial on how to implement these neural networks in the context of GEM, in the context of stable baselines. Okay, so next, just after the break, we are going to see this in here. Okay, and this idea is called eligibility traces, and this is it gives rise to what we call sometimes generalized advantage networks, and then we are going to see this after the break. We are going to have a break now, but it's is there any question before we go to the break? No questions? Okay. So now is 4:02, 10:02 here for me. So let's do a break until 10:20 or 4:20 for you. And then we are going to start with eligibility traces. Okay, so I'm going to stop my camera and stop my microphone. So like 4:20, we start again. Okay, so we're going to continue, and as I mentioned before, we are going to see now a way that we are going to create, sorry, a generalization between temporal difference and Monte Carlo. So this is going to be our objective in this part of the lecture. And this is we're going to use something that is similar to this when we talk about more modern methods. There's a different name that is used in there, but it is something that is very similar to this. And it is something that is very powerful and something that we need to take into consideration when we are developing these new methods. As I mentioned last time, everything that we've seen so far has a direct implication in the ways that we do this in modern applications of reinforcement learning. But these are like the concepts and the basics that you do need to understand, because if you don't understand this, then you're going to try to make your system work, and then your system is not going to work, and you're not going to know why it does not work. Okay, so I mentioned this last time, that we can make a system to be as deep as we wish, right? Most of the time, when we use the temporal difference, what we are going to use is a one-step TD, also called TD0, right? So these are the same thing. One-step TD or TD0, this is the same thing. So this means that we have only one step here. So we are in a state T. We are going to choose an action, and then we are going to go to state T plus 1, okay? Where T here is the index that we are going to use to represent where we are right now, okay? So this is it. However, I mentioned this last time, that we could use more than one action. So we can actually go from state T to state T plus 1 to state T plus 2. We can do this in 3 steps, okay? We can do this by n steps. So here we get st plus 1, st plus 2, st plus 3, plus 4, up to st plus n, right? So that would be the last one here. Or we can actually generalize this to a Monte Carlo approximation, so that we start at st and we go all the way to a terminal state. The number of steps that we have in here is going to be variable. So it depends on the application, it depends on that particular run, but that's what we are going to have in here, okay? Observe that each one of these, they have their advantages and disadvantages. The advantage of TD0 is that this is going to create an update that is much faster. The advantage of Monte Carlo is that this particular approximation, since we are going to calculate all the returns, is going to be unbiased, right? Whereas, like all the other ones, they're going to be kind of biased, but this bias is going to reduce as we keep doing this for longer and longer time frames, okay? We can represent this as our equations, right? So we have seen this like for Monte Carlo. In Monte Carlo, we go from like the first return, the first reward, all the way to the last one, where we reach like a terminal state. And this is going to be our return. And our return is going to be based on a sample that we actually took, right? In TD0, what we are going to do, we are going to simplify this so that we can do bootstrapping. So our return is going to be based on only the first reward plus the value that we estimate for st plus 1. And then we've seen this last time, that when we do this, we have like more updates, and these updates, they are faster to create convergence in our system in most cases, okay? I also mentioned that we could like do this for more steps. Let's assume that we want to do this for 2 time steps. So now we have the first reward, the second reward, and then we have the approximation of the value. So now we have more rewards that are going to create the approximation of my return. This approximation is a little bit better than this approximation here, okay? However, it takes more effort because now I have to keep track of these values. And keeping track of these values is something that is going to cost us, right? The other thing is that it's going to be way harder for us to, in this particular scenario here, to create samples that we can use in modern GPUs, right? Because now we have to have like all these different conditions that we're going to use. We can do this for any arbitrary period. So here is 2, but we could do 3, 4, and we can generalize to n. And as I mentioned before, so now we have all the rewards, and then we approximate the value at st plus n. So it's the nth visit to the state in the future. And then we can do these estimates, like the state value estimate, using these approximations here, right? So we can actually use this, and keep in mind that we could replace this for gt t plus 2 plus 1 plus 3, or if you just put gt, is going to be the Monte Carlo return. So we can actually do, this is a generic way of doing it. So eligibility traces creates a way for us to unify these two ideas. So now we are going to have the Monte Carlo and the TG approaches unified through another parameter. So the cost is that we have to define a different parameter, okay? And this is going to be done through a parameter that we called this lambda here. And that's why we call one-step TG TG0, is because in that particular case, our lambda equals to 0. If lambda equals 1, so we go all the way to Monte Carlo. And in values in between, we are going to have a mix of like a TG0 and Monte Carlo, okay? So we have going to have like a both. And now we are going to be able to create this, to create like a better approximation of what this value is going to be. And this is a way for us to avoid our system just being short-sighted. So that's the idea. And this is going to also come at a cost that we are going to create a short-term memory vector that is going to be of the same dimension of the long-term memory vector. So I'm using this notation here just because later on we are going to use it. But in our case, like this Z here, it's usually called E, right? And this W here is going to be our V or Q, okay? So these are going to be the two values that we're going to use. So E and V or Q, so they're going to be of the same dimension. And here I'm saying G because it can be like the number of states, it can be the number of states times the number of actions, so it depends on what we are going to do, okay? This can be conceptualized also as a decay factor. So it's a factor that is going to go from 0 to 1. And note that we can actually have equal to 0 or equal to 1. If we have 0, so we have TD0. If we have equal to 1, we have Monte Carlo. But everything is on the same page here, right? And this is something that we are going to see later on when we talk about these advantages calculations. So we're going to see this later. So we don't need to save the vector of returns as we do in the n-step methods. And observe that in this n-step method here, we need to save all these rewards, and we need to save the returns as well. So this is costly memory-wise and also algorithmic-wise, because then our algorithm is going to have, like, you know, some if-then statements. so that we can actually make this work. Okay. And again, this is just like for us to create like an approximation, but in our case, this is going to be just a V of ST plus N. But if you assume that this is going to be dependent on a table, like in our case, is going to be the whole table, or some parameters, like when we do neural networks. So we're going to have like this particular return here. So in this case here, we are using just a single return. But observe that we don't need to do that. We actually can do that for more than one return, and we can combine them. If this is an average, so this creates a better approximation of what is going to be the combined return. So there are different ways that we can do that, right, for different values of n. Let's assume that we want to create a generalized return, and just keep in mind that this term like generalized return or generalized advantage is going to come back later. Okay, so here we have like a return of 2 steps and a return of 4 steps. We can create this return, and we can use this same algorithm as we are using here, like in this last line here. We can do the same thing by saying that my return, and then here I'm just going to say that this is going to be my return P is going to be equal to this. Okay, so now I have half the weight for this and half the weight for this. Okay, so now I can use the same idea. So this particular return here is going to create an approximation of that. Observe that since this is an average, if I add these 2 coefficients, I have to have them adding to 1. So that's a requirement. Otherwise, this is not an average, right? So if this is less than 1, so we are going to attenuate these values here. If this is greater than 1, so we are going to amplify them. So they have to be equal to 1. So that's a requirement. And we can do this. In this case, we are doing this for only 2 trails here, but we can actually do this for more than 2. And we can do this for any number of values that as we wish. So for example, we can actually define this equation here, which is the exact equation that we use for these returns. And in this particular case, we are going to have one coefficient, like 1 minus lambda, that is going to be for the first value, and then we have for the other ones. Observe that, like, for example, let's say we start at n equal 1. So at n equal 1, so this is going to be lambda n minus 1 to the power of 0. So whatever number we have at lambda, this is going to be 1. So the first coefficient is going to be 1 minus lambda. So this equation works even if lambda equals 0. Okay, so even if lambda equals 0, this actually works. And then we are going to have a decaying value afterwards. So the first return is going to have a weight of 1 minus lambda. The second one is going to have a weight of 1 minus lambda times lambda. The third one is going to be 1 minus lambda times lambda squared. And we keep going, right? So we keep going all the way to the end. And the end can be when we get to the terminal state. Okay? So we can see this graphically. So this is the way here. Okay? So that we can get this lambda, and the way that these values are going to decay, they are going to be dependent on the value of lambda. Observe that if lambda equals 0, this is going to be 1, and all of these are going to be equal to 0. Okay? Observe if lambda equals 1, all of these equals 0, and this equals 1. So therefore, that's why we call this TD0. We usually don't call Monte Carlo TD1, but we could if you wish, right? But it's not a necessity. Another thing that we went over this like in a previous lecture, but it's you can convince yourself that if I add all these numbers here, these numbers are going to add to 1. So if I put like 1 minus lambda plus 1 minus lambda times lambda plus 1 minus lambda times lambda squared all the way to the end, it can be this end here, or it can be infinity. It doesn't matter. This is going to be equal to 1. Okay? So that's another thing that you have to take into consideration. So we are creating a way to generalize this return to consider all these intermediate values, right? All these intermediate rewards there, or returns there, okay? And then this is going to be a parameter that you're going to choose for your eligibility trace and for this generalized type of return. So, and this is just going to be a combination of all of these particular conditions all the way to Monte Carlo. And we can actually do this for, like in n-step SARSA, we're going to do this for each one of these separately, but now we can combine all of them. And another thing that is important to understand here is that here we are decaying, right? Because this value is going to be larger than this, that is going to be larger than this, that is going to be larger than the next one, and all the way to the end. And these values are decaying in an exponential rate, right? So lambda here is going to be a rate of exponential decay. So that's why I said that this, you can call that a type of decay factor, okay? And it is exponential, so the curve is going to be exponential. And these values in here, if you discretize, so they're going to be related to the weight for each time step. So this time step, the first time step, like the first return, is going to have a higher value or weight than the second one, than the third one. And this is going to be decaying by lambda. And when we get to the final state, the terminal state, so this is going to be the remaining value, okay? So you can think of these as this integral here that is going to be related to the value that is going to be of more importance, sorry. And the area under this curve is going to be equal to 1. So that's another interpretation of this. So it's the same way, okay? So we can write this in terms of like all these returns, and we can actually see what is going to be the effect, right? So because now if we consider a terminal state, so this is going to be the weight for the terminal state, and this is going to be the weight for each one of the other returns that we have. So sorry, the terminal return, and then all the other returns that we have. So different ways of seeing this. So you might be like, it might be better for you to observe this with this format, or this format, but they are all the same, okay? So they are exactly the same, and they give you the same insight, but you might be better off in one case or the other, okay? In our case, so what we do, we create these updates in here. So what it means is that the first return, like this is what we call the forward view, is more important for you. Then the second return is a little bit less, all the way to like the terminal state. So this is a forward view. And this algorithm, like as if it was written like this, so, and again, this is just a generalization of the algorithm that we saw before, where we have V of ST plus 1 equals the previous V plus alpha, the return, and the V itself. And then here, this would be equal to 1. But this is just a generalized way. And I'm writing this way because later on, we're going to use this like in a future lecture. Okay, so here we are looking of all these different values. And then we are like, as time goes by in the future, so we are going to take more into consideration the previous, the first return, than the long return. And the reason why we do this is because the first return is more certain than the last return from the perspective of where we are in this state here. Okay, This is an improvement on how we do this with the other algorithms. Why? Because it's going to update this weight vector at every single step. And these computations, they're going to be equally distributed in time. So we are not going to create this in a way that is going to be different for each one of the situations, right? Because the algorithm, as before, since we have like all these different conditions, so there will be different computation times for each one of the steps. In this way, we have all the computations to be equally distributed in time. We can use this also for every time of problem. We can use this for continuing problems, for episodic tasks. We can do that, everything, right? And recall that these numbers here, like they have the same number of parameters. Therefore, there is a cost. And this cost is going to be linked to the storage that we can actually have in the system. In this particular case, we are going to double the size of our storage. And because we need to save this. Now, how this is done, we can initialize all these values in this table here equal to 0 in this parameter vector there, and then we create this update here. When we do this for a tabular version, so this, again, this is the generalized version, that we can do this for whatever the gradient here is going to be, right? So, and this is, we are going to see that this is like what we do in neural networks, like after your vacation. Right now, if we are doing this in the way that we are describing here, and this is going to be the same dimension as we had before, so this vector here, or sorry, this gradient here is going to be equal to 1, and we just add 1 here, okay? Because this is going to be, well, what was I visit this state. Therefore, since I visit this state, I need to put a 1 there. So that's the idea here, okay? So these parameters, they are going to generalize the visits that we have. And this is going to include if we have contributed this positively or negatively to the value function, because this is going to be linked to how the value function is going to be updated, right? It's going to be linked to the value that we are going to get in the TD error, for example. Another thing is that, look, here is even more explicit that this, we are going to look at more recent contributions way more. Observe that if you recall, like gamma is a number that is less than 1, and lambda is at most equal to 1. So when we multiply a number that is less than 1, and let's generalize this to be a number less than 1, so when we multiply these two numbers, so then we get these different values that are going to be, this multiplication is going to be even smaller than that, okay? So this dies off like very fast, depending on the values that you're choosing here. Also observe that if we use this value here equal to 0, we only use the current information. And therefore, this is TD0, this is a one-step TD, the same way that we were using before. This vector here is going to keep the eligibility of each one of these components into the weights, right? So if we're using the TD error, so what we are going to do, we are going to calculate what the TD error is, and then we are going to multiply this by the eligibility traces, right? And the eligibility traces, like E here, is going to be represented as the Z. So recall that before I said that when we have a table, we call this E, okay? But it's the same idea, okay? So one is just the generalization of the other. And if you look at the values here, as I mentioned, when we have a table, so what we do, we calculate what our TD error is, and we calculate our eligibility trace. And this eligibility trace is going to be the previous value plus 1. So that's what I had written there. Now, we are going to make it decay with this parameter there, okay? But we are going to do the update based on what this value here is going to be, okay? So now we do the update, and then we apply the decay, and then next time, this is going to be a smaller value. This is preferred to this. The reason why this is actually not easy to be implemented is because we are looking at the future, right? So we have to wait for the future for us to do the update. In this case here, because we are using this information here, this particular algorithm, we are actually technically looking at the past. We are not looking at the future. So what we can see is that that's what we are doing, right? So we have like this TG error that is propagated into the past. And here since this is a causal system, we can implement this at this particular moment in time. And then we can use this information to do our updates. Why does this work, right? Because it's technically not the same thing, right? So one thing is like you looking at the future. The other one is looking to the past. So looking to the future, we have what is called a non-causal problem, right? Because you have to wait until the future, for you to actually do your update. This is a causal problem because we are looking at the past. But the implicit assumption here is that the future is going to work similar to the past. Okay, and again, this is nothing new. We have been using this forever, right? So in engineering, in computer science, and specifically, we do this in neural networks all the time. So that's why we have training sets, training data that we use. The assumption is that the data that we are going to see in the future is going to have the same distribution as the data that we saw in the past. So that's the idea here. So it's a very interesting idea, but this is why this actually works, right? And again, it is not new to reinforcement learning. It is used in everything that we do in engineering, in computer science, as I mentioned, in science in general, right? So that's kind of the principle of induction. So we assume that the future is going to be equal to the past. If the future is not equal to the past, this is going to fail, okay? But then you say, okay, so that's a problem of reinforcement learning. No, it's not. It is a problem of everything that we do. If the future is not the same as the past, or does not resemble the past, then we have an issue. Everything that we try to predict is going to be wrong, okay? So just keep that in mind. So, but this is an algorithm that can be easily implemented. So we can implement this. We don't need to wait for future information. We don't need to keep track of these updates. The only thing that we need to do, the cost, is that we have more storage, in this form here. But the algorithm is of the same complexity every single time step. So if you calculate the complexity here, it's going to be the same for every single time step. Okay? Now, let's compare that to this n-step SARSA. So here is different, right? So if you look at this, we have these loops, and then we have to keep a track of how many time steps we have actually had in the future, and then we have to create this auxiliary variable here. We have to keep track of this with an if statement, and now we have this if statement, and then the complexity of each step is going to be dependent on what these values are, and this is going to be much, much harder for you to implement in a computer, and it's going to be much, much harder for you to make this an efficient code, okay? And that's one of the reasons why we usually don't do that. So, but this is just to show you that by using this n-step SARSA, that is using this idea of generalizing the values, even though here we are not generalizing, right? So here is just for one value, n. Let's assume that now we have that idea of this lambda error in the future. So you would have to do this for every single step. That would be prohibitively complex. if you're doing this in your computer. So, but using the Sarsa Lambda algorithm, so that's actually way more efficient, because now we can implement this by the generalization that we had before. Okay, so so this is going to be the Sarsa Lambda would be very similar to the TD Lambda, but now the only thing is that we do need to describe what the values are going to be. Okay, observe, like recall that here I'm just using this as a generalized version of the system, and again, it's just because we are going to pick this up like next class. In our approximation now, these are going to be directly the Q values. So instead of being this, so here is going to be Q. This is going to be Q, but it's the same equation, right? So it's a so you understand that that's the same thing. And here, this is going to be equal to 1. Okay, so it's a multiplication by 1, but it's the same equation. And here, again, this is going to be Q, this is going to be Q, and this equation here is the same as this equation here. Okay? Same thing. You can later on go to the notes and then take a look and make sure that they are the same. Okay, but this form here is more generic, and we could use this with a neural network as well. We could use this with any function approximation that we wish. Okay, so that's going to be very powerful. The backup diagram for Sarsa is the one that we have already seen. So we have like all these different updates in here. Okay, now the only thing that we do is that we generalize this looking at the past, and then this algorithm is going to be more efficient in that way. Therefore, in this particular case here, so we are going to have the same thing as before, but this, we are going to say that this equals to 1. Okay, these are going to be the values that are going to use, the E values that we're going to use. We initialize this equals to 0, and then we do the updates. If you look at the algorithm, so the algorithm is going to be something like this. So this algorithm here is the same as we had before, but we replace the V with the Q. Okay, so that's the only difference. And by now, you should be convinced that we can use one representation or the other. We usually use Q because it's more efficient, but we can use one or the other. Okay, this is going to be our update, right? So sorry, our eligibility trace that is going to be used for the updates later on. So this is going to multiply by how much we do these updates here. Okay, so that's the only thing that this is going to be. And we keep track of this, and then when we choose the action, so when we are going to choose an action, we are going to take into consideration the epsilon greedy algorithm that we have seen so far. So it's same idea, same approach, but now we have a generalization of how we do the updates. And these updates are going to be weighted by this value of E. Observe that these values here, they are going to be always decaying, but we are going to take that into consideration for the updates that we are going to be doing. How does that work? So like in practice, let's see how this actually works. So here is like that problem that I presented last time. So we have these wins, and then we start here, we go all the way to the end, and then I mentioned that this is going to be the optimal path that you're going to take. So regardless of what you do, you're always going to end up in this location here, and then from here, you have to find your way to the goal. If we do this with a one-step Sarsa, what is going to happen? It is going to happen the same thing as I mentioned before. You're only going to get an update when you go this way here. Okay, so when we get to the goal. So therefore, if we look at the path that is generated, it is going to be something like this. But if we have like a one-step Sarsa, you're only going to get like this update here. If we use a 10-step Sarsa, what is going to happen? as I mentioned before, right? So we are going to get like this trial here, or this trail here, all the way here. So from here on, we are not going to learn, right? Because this update here is not going to be back propagated to all the way here. That's the reason why, for example, the 10-step SARSA it is technically like going to be faster in terms of updates. But in practice, this is going to be so much harder for us to implement that this code here is not going to be efficient. If we implement this eligibility trace idea, we have something different, right? Because now what is going to happen, depending on the parameters that we choose, like for Lambda, what is going to happen is that we are going to get the return propagating in the past all the way to the beginning. Observe that this is going to be attenuated all the way to get to the beginning. So it's not going to be the same as before. However, it's not going to have like a hard stop, right? Here we have a hard stop, here we have a hard stop, and that's it. So here, no, we keep going this. And this is why this is called the generalized return, because now the return is going to keep going back all the way to the past. And this is tuned by the choice of lambda, right? So if we use a lambda that is 0.9, so that's what is going to happen. If we use a larger number, so of course that this is going to go way fast in the future, in the past, sorry, way farther in the past. If we use a smaller number, so this is going to be cut off like a before. And there are reasons and there are situations where we should use one or the other. So it depends on how we are going to set it up, okay? This is a very, 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 very powerful idea. It is something that we are going to, again, look into this later on, specifically when we look at like a more modern algorithms, like in policy gradient, which is like something that we use quite commonly like nowadays, okay? So these effects in here are going to be felt way in the past, and it's going to avoid that we are going to create like these types of like ugly settings and ugly if statements like this, okay? Which in general makes our algorithm way less efficient and much harder unnecessarily to be implemented. Okay, I'm not saying that this is a bad algorithm. I'm just saying that there are problems with efficiency within this algorithm. Okay, there are different ways for us to implement this. So one idea that there are different versions of this TG lambda. There's one that is called the Watkins Q lambda. This is a very popular implementation. The idea here is that when we take a non-greedy action, we are going to restart the eligibility trace. And the reason that we do this is because we are not following the policy any longer, and therefore this is going to be a problem. And this is what is called like Watkins Q lambda. It is the way the most common implementation of it. You see these implementations, for example, in DQNs. You can actually have that set up like in DQN, but it is not something that it's that is unique. So there are different versions of it. I'm mentioning this in here just because when you go back and then you want to do some work by yourself, you're going to see that there are different implementations of this algorithm, and Watkins Q lambda is one. And then what happens is that when we have like the first non-greedy action, so then you reset the value. So this is how this is actually done. You keep doing this in the same way as you were doing before, but when you have a non-greedy action, so this is something that you do, and then you restart your learning from that point on. So it's a way for us to implement this. Now, to finish like this portion of the course, right? Because all of this is using tables, right? as I mentioned before, the use of tables is not the most efficient way for us to solve this. And there are lots of reasons for this. But the ideas, the techniques, they are the same, regardless of what you're going to use in the future. You need to understand this in order for you to implement efficient algorithms, okay? There are like recipes, like you can go like to websites and you can get ways to solve these problems, like, and then you can solve maybe 80% of all the problems that you could use reinforcement learning on. But since you're taking this course, you're taking this degree, what you want is not to solve like the 80% of problems that anyone can solve. You can try to, you want to try to solve the 20% of problems that they are hard for you to solve, right? So that's what this is about. Let's revisit that example that I showed you before, like this learning using like the swarm, right? So this is the same problem as we have seen before. And then I want to show you everything that is actually implemented in here and how we can take advantage of all these problems, right? So this is an older work that we've done. Like it was all based on tables. It's well cited, like lots of people cite this work because this actually puts together lots of different ideas. And to the best of our knowledge, this was the first time that anyone has done this, like has put like all these ideas together. So if you recall, what we have like this learning objective in here that is going to be the minimization of this cost function, which in our case, like as I mentioned before, it could be a maximization as well. So it's just the dual problem. But we use this Q-learning idea, and this Q-learning is going to be based on this table. So we have this table that is going to be updated based on information that we have from the environment. So this is a very high level view here. So now you can understand what is the loop here, right? So we have a state, we have the cost, right? So we'll have the state, we have the reward. So this is the environment. We send an action to this environment. We observe the state, we observe the cost, and then we have an agent that is going to update these entries on this Q table based on that. For you to find what is the best solution, you just go to the table and you find what it is. And this, again, this can be a very high level thing. This can be like a neural network, but in this case, is a table, okay? So what are the innovations that that can be done here? And then to put all of these together that we have discussed so far in this course. The first thing is that we can actually use these ideas of this Q lambda, right? So this is a different version of Q lambda that is called Banks Q lambda. And we can also have a variable learning rate. So these are two ideas that were put together in this paper, which is something, that we are going to solve a problem that most people cannot solve, because if you just follow what people have done in the past, so this is not going to work, okay? So here we are going to use these updates that are going to use, instead of just a one step, we are going to use the idea of eligibility traces. So this TR here is eligibility traces. Then what I can do, I can create like these eligibility traces very similarly to what we have seen in this course, okay? So this is +1 if this action here is the same one as we chose, or otherwise I put a 0 here and I just create a decay, right? So that's the difference between these two here, okay? So this is using these ideas. On top of that, we use a variable learning rate, meaning that if the errors, like these errors here, they become bigger, I will restart this learning rate, okay? So again, these ideas, they have been floating around like differently, but it's to the best of our knowledge in the sense of like a decision making for actual vehicles. That was like the first time that people have done this. Okay, so this was the second innovation that was put together in here, and this gave us like this algorithm Q flocking that creates this flocking. On top of that, what we have done, we have used this idea of planning to make sure that we can actually learn faster. So now I can like we expanded this so that we have a model learning approach here. So this model learn is what we saw today. This is planning, right? So based on that, we can create updates here that are going to be through planning and through learning. So this is a direct update. This is an indirect update, right? So we can actually take all of this together, and then we can run this in the environment, and then we can get this. With all these different innovations, that's why you can actually learn this in this particular fashion, right? That I showed you before. So observe that the number of episodes that we use here is relatively small. So we don't need a lot of interaction with the environment. Why not? Because we actually are using this indirect way, using eligibility traces that are going to actually propagate this way past in the way farther in the past. We are tuning the learning rate to the problem that we have, and then when we put all of this together, we get this learning that can be done very fast, right? Haven't we done this like in this way, this would not have been solved in this fashion. So if you look at like episode 20, this is a very decent result already, right? And then if you do this like for episode 30, this is really, really good. So we actually made this thing work in a much faster way than people have done in the literature. So the idea was that in the literature, if you used dynamic programming, this would take literally days to run, okay? Like several days. And the results would be worse than this. Then if you use just reinforcement learning the way that everyone used, so you'd still take days to solve for this. By putting all these ideas together, planning, like eligibility traces, tuning the learning rate, we transformed this like from days to a couple of hours, right? Even like we didn't use like a GPU for this, we used actually a CPU to do this. Nowadays, with the CPU, you can do this in few minutes, right? So that's how much faster this is done. So this is something that you should keep in mind, right? So what you're learning here is not just for you to replicate and solve like a simple problems, but it's for you to generalize and try to solve like harder problems. So that's the whole objective of this. And again, even though you would not solve this with tables anymore, right? So you would solve this with different approaches. The ideas are the same, okay? They are just going to be implemented in different ways. You need to understand why you're doing one thing against like doing other things. So summary here for eligibility traces is that this is a generalization of Monte Carlo and TG methods. So you can put all of them together. Using this, you can speed up learning. Or another way of saying this as well, you can stabilize learning. So after your break, you're going to see that this is something that actually exists. It's something that can make your learning way more stable than if you use different techniques, okay? There are several implementations available. I'm not saying that nowadays it exists like in this particular fashion, but it's it's used in a way that is similar to this. Okay, and we use this for function approximation. So if you're doing this for function approximation, so using neural networks, this is going to be even more efficient. We are going to see this in the near future. So next lecture, so this exactly like next lecture this Thursday, we are going, as I mentioned before, we're going to have a tutorial. This tutorial is going to be for us to go over the some things for the assignment that you're doing, and also like some ideas that you are going to be using as your project, right? So we are going to go over in GEM and in stable baselines or a similar framework, how you can actually put these ideas together, and then how you can create like very easily a neural network, and then how you can plug the neural network into your system before we see like the theory, right? So I'm just trying to speed up things so that you see in practice how this is, understand a little bit what the issues are, and then we are going to investigate the theory. After this, like after this coming Thursday, we are going to have a week break, right, for your vacation, and then after that, we are going to start looking into new methods. So these new methods, they are newer, and in practice, they are the methods that everyone implements, and they do not use tables. However, like you have to understand how these problems are solved, so you don't reinvent the wheel, right? So it's something that you do, like everything that we learned so far is important. This is all the mathematical basis for you to actually solve these problems, okay? We use that specifically because the problems that we want to solve nowadays, they are large, right? So we have these large state spaces. We have large action spaces. And if we don't have a way to generalize the solution, we will not be able to solve them. Okay? Even though these ideas, all the ideas that we follow up so far, could, in theory, solve those problems, in practice they cannot. Right? It is just it's not possible. Okay? You would have to have access to a computers with way more memory than we have, and way faster access to memory than we have, with way more powerful processors than we have. And even in those cases, right, even if we had that, using function approximation is still better, right? Because you can generalize for a lot of different solutions. And the reason is because the environments that we're going to deal with, they are not environments that are deterministic. So depending on what you do, you get like so even if you do the same thing, the results are going to be different. So they are stochastic in nature. Therefore, it is better for us to use these approximate solution methods. And one of the most important methods that we have to do that are neural networks, right? So that's why we are going to use this in this fashion, in this way. Okay. So next lecture, which is going to be like this Thursday, we are going to do a tutorial, and this next lecture that I'm meaning here is the one that is going to be after your break. So we are going to I think it's going to be already in June, and then we are going to look into these different solutions. But on Thursday, you're going to see like different solutions, different ways on solving this problem, how to build this in your computer. And we are going to also talk about a little bit of the projects that you're going to be doing, how you can actually speed up your updates and these types of things. Okay. So we are going to stop here today. Is there any question on the material? No? Okay. Next Thursday, this coming Thursday, you're going to meet with the TA for this course, Mateus again. So we have developed, I think it's an interesting tutorial for you. And also you can have like a discussion about the project, about like other things in the course that are more linked like to the implementation. Okay. So again, make sure to come, make sure to talk to Mateus. That particular tutorial, I think it's very important for you to have a more interactive way of doing it, right? So the lectures you could technically, maybe watch later, and then that can actually help you. But if you're doing like things like in solutions, if you're not participating, it might be very complicated for you to realize what was happening. Okay. Okay. Any comments? Any questions?
Thank you so much, Doctor.
Okay. Thank you. Okay. So again, like a Thursday, you're going to see Mateus. Enjoy your vacation next week. I understand that it's going to be good for you, right? So to have some time off. If you have any, and as I mentioned before, the course I changed the course so that like all the deliverables are delayed as well. So you should like next week should be vacation for you, right? So it's if you want to work, you work, but it's not something that you need to do. Okay. Okay. So thank you very much. I really appreciate your time today. If you have any questions, so please just let us know. Keep track of like the deliverables. The deliverables are important. Okay, so but everything is already set up in the system. Next class, Mateus is also going to talk to you about like the project proposal. He's going to be able to give you some feedback on that as well, and then I'll see you in a couple of weeks. Okay. Okay. Thank you very much.
Thank you so much.
Thank you.